And secondly, a recording of this session will be available in approximately 48 hours to attendees. So with that, I will turn it over to Professor Ito.
Thank you so much. So thank you for coming. I will talk about this title, Renewable Energy Expansion, today. Just for one logistics, if you have any questions, you can put into chat, and Blake will ask me on behalf of you. So any question, that would be great. I think that would make the lecture much more interactive. So feel free to put any questions. Okay. And also at the end of the lecture today, we're gonna talk about the new master's program. So please stay tuned until the end. Okay. So this is kind of overview lecture I put together about how we get the renewable energy coming into the world. So I want to start with this motivation. If we think about climate change mitigation, electricity is a big part. One, because from greenhouse gas emissions view, about 20%, 25% in the US greenhouse gas emissions come from electricity sector. And this number is very similar between different countries. Also, another interesting and also very exciting phenomena right now is, as you know, EVs are coming. So another large sector in terms of emissions are transportation, cars, trucks, and other things, and which will be electrified soon. So that means we're going to use more and more electricity. And there's another one just coming in recent years, which is data centers. So AI, data centers, they are going to consume more and more electricity. And for the first time in the long run history in the US, we're going to see increasing electricity demand a lot in the next coming decade. So electricity is becoming not the boring sector, actually very exciting, interesting sector. But we also know that a lot of electricity comes from coal-fired power plants, other type of fossil fuel power plants. So like if we increase electricity but burning fossil fuels, then it's not going to be helpful for climate change. So the question is, how can we get solar, wind, potentially hydro, like those type of zero emission electricity, and potentially another one is nuclear. But today's talk is more focusing on solar and wind. Okay, so solar and wind, maybe if you are like my age, back then, this was maybe around 2010, 2011. I finished my PhD in 2011. I remember when I was doing PhD, I talked to my advisors, and how about if I study solar and wind? Would it be cool? And I think many of the professors' response back then, 2010, was, Koichiro, just don't waste your time. Wind is expensive, solar is even more expensive. So it's not going to come into the market. Without subsidy, we can't just use those technology. I think many professors talked about that way because of this figure. So if you look at solar on the right-hand side, if you look at 2010, solar cost, this is what we call levelized cost. So like lifetime of solar plant, fixed cost, variable cost, including everything. What is kind of roughly speaking average money we have to spend to get 1 megawatt hour of electricity from solar? And it used to be this number was like $500. Okay, and to give you just some perspective, if you use natural gas power plant, it's about like $35 per megawatt hour. Okay, so that means like $500 solar. Okay, let's forget about it. It's not going to be available for many parts of the world. That was the case in 2010. Wind was a little better. It was close to $200. So maybe with subsidy and everything, that was okay. But still $200 versus $35. So don't worry about wind either. But the thing has been changed a lot because of technological change. also learning by doing, massive large-scale production, mainly in China, solar panels and then wind turbines, right? So we are in a very interesting time period because of this technological progress. And in our study, like economics of renewable, economics of environmental like issues, we basically think about like why this happened. I already said something about learning by doing, technological innovation, maybe competition among different countries, different firms. Like we do research on like this type of topic. Okay, so I will talk about a little bit about it today. But basically, like very big picture point is now this is great news. Solar and wind are now actually very competitive. So now 2022 and now 2025, so it's actually even better. It's about close to like $35 now. So it's you can think about in terms of levelized cost, wind, solar, natural gas power plants are now pretty competitive between each other, which is a great news and very different from 2010. Okay, but if you look at, next slide, yes, how much we have solar and wind, okay? It's interesting that we are not getting there yet, okay? So if you look at like Denmark, it's fantastic because they have a lot of wind farms. Actually, this is, I was also surprised. Denmark now gets 70% of the electricity from solar or wind, mostly actually from wind, right? So already 70% coming from clean energy. But if you look at the United States, it's still less than 20%, getting better and better. China, Japan, also less than 20%. Chile is around 35%, and also like you can see like a very steep increase. This is coming from solar, which I'm going to talk about today. So the point here is we are doing much better, but still not there, even though the cost is already good, right? So there has to be some other reasons, like which we do research, study, and also teach at high school. So we want to talk about like why this is still not there. What's the issues about slow kind of expansion of renewable energy, and what can we do? Okay,
Professor Ito,
go ahead.
we actually have our first question,
Great.
which you may be leading into from Mitch, which
Yes.
his question is, how has the scaling of critical mineral production contributed to declining costs of renewables, and have there been any causal studies connecting these?
That's a great question, which I don't have a great answer. So I think probably my guess is yes. Okay, but I don't think there is a good study to connect, cost reduction in a mineral. I think mineral extraction. I think probably the question is talking about, like materials for solar panels, right? I think we have a lot of studies talking about the production gets more efficient, more cheaper, large scale, but the extraction of the minerals, my guess is there is something going on there too. Great point. I don't know. I don't think we have any research. My colleague Ryan Kellogg is expert on natural resources, so maybe I'll ask him. That's a great question. Any other questions so far?
Not yet.
Great. Okay. Please ask in the chat if you have any question. Okay, I would appreciate. All right. So 3 things to talk about today. In my view, there are those obstacles we need to kind of get through. The first one is underdeveloped regulatory and market design. So if you think about regulation, like energy sector regulation and energy market design, okay, basically we built everything in the last like 100 years, not thinking so much about renewables, right? Because we have been using fossil fuel, coal-fired plants, oil power plants, nuclear, those type of technology. So all the regulation, market design were designed for those old-fashioned, in a sense, power plants, okay? Maybe I shouldn't say old-fashioned, it's fossil fuel power plants, which actually have a lot of benefits, okay? I will explain, but just quickly, the best part of the fossil power plant is we can predict very well, we can control very well, right? Suppose you have natural gas power plant here. We already have a pipeline coming into the power plant. So how much natural gas we want, how much we want to produce today, we can plan, also predict, and also we can change. If there's demand shock somewhere, we can increase the production. If there's demand shock negative somewhere, we can decrease production. Like it's very easy to control, even in the last minute, a little bit, okay? If you think about solar and wind, that's almost opposite, right? It's a great energy source, clean, marginal cost zero, but like, can you predict well? We can predict a little bit, tomorrow's solar, tomorrow's wind, but uncertainty is still big, so we cannot predict 100% well. Also, we cannot change in last minute, right? Can we ask solar to come a little bit more? Or can we ask the nature to blow wind a little bit more? No. So that's the hard part. Okay, so the first part is basically those regulation and market designs are a little behind. So I will give you some example. Okay.
Another question,
Okay.
which you may also be leading to from Takashi. He says, I respect renewable energy, but if wind energy is competitive, why do they still need subsidies like REC, OREC, and ITC?
Good question. So here's an answer from an economist, okay? From just purely economics perspective, setting the political economy aside, if wind is perfectly competitive, maybe there's an argument to make, we don't need a subsidy. We shouldn't subsidize, okay? We let them compete in the market, okay? There's still economics argument to do the subsidy for at least two reasons. One is the market failure coming from technological innovation, okay? We might want to push wind energy to get technology advancement more and more right now, because that will be helpful for the future. But if we don't subsidize, the benefit is going to come to the future. Like everybody gets that benefit. But the technological advancement, some companies need to do R&D, right, to have better wind technology. It's costly, but they are not the only one who's going to benefit from this technology. Everybody else in the future will benefit. So one argument to do the subsidy is this technology, like R&D subsidy, usually makes sense because that's going to benefit everybody else in the future. That's one. Another one is kind of similar. I already talked about learning by doing. Okay, maybe there is a learning by doing. So if we do more and more production of wind now, that would decrease cost a lot in the future. So maybe we want to help the current wind players to do it. So those are the economics reasoning. Potentially, we might be able to justify subsidies for wind and solar. In reality, to my mind, many of the justification just comes from politics. Okay, so politically, solar and wind are kind of popular industry, and those industry, pushed politics, postal politics to get more and more subsidy. So we need to be careful between politically, we need a subsidy to push versus economically, from economics perspective, we actually want a subsidy. Both of them are important in a sense to think about the policy design. And like here, like when we study this type of issue, we want to kind of separate and think about those two things, both of them. Any more questions?
There was just a more of a comment from Adrian who mentioned, aren't fossil fuels also subsidized?
Exactly. Yes. So the question is, do they need subsidy? Maybe for R&D, learning by doing, but maybe their technology is already there, so maybe they don't need. And also there's another argument. If we want to push the carbon emission down, do we really want to subsidize fossil fuel. So maybe one thing I forgot to mention is another reason maybe we want to subsidize wind and solar is the environmental externality coming from pollution, right? Because we don't have like a carbon tax or basically market mechanism to price emissions, at least in the US. I mean, EU has EU ETS. Some parts of the US have something similar, but the nationwide, we don't have carbon tax. So that's why we might want to subsidize solar and wind. That's another reason, economics reason why we might want to subsidize renewables. So this slide I already talked about, right? Conventional power plants. It's interesting if you look at Chicago. If you come to Chicago, there's a cool fossil fuel power plant in the city. Okay, if you go to like West Loop, a little bit to the west from West Loop, or maybe Pilsen area, there's a I think it's coal or natural gas power plant still sitting there, and they operate some days a year. So traditionally, we put those power plants close to the city because we know city needs electricity. And for fossil fuel power plants, we can do it. But renewables, we cannot do it. That's one like challenge. Another reason is renewables are intermittent, uncertain, I already talked about, okay? So one example coming from the paper I like, this is not the paper I wrote, I wish I wrote, but this is a great paper from this author, still working paper, very new. They talk about interconnection queue in the US, okay? So interconnection queue problem is one example of the regulatory kind of underdeveloped regulatory design. So in the US, if you want to create a new power plant, first thing, probably you need to talk to the bank, right? I want to build this power plant here. Can I get the money? Usually they borrow money from financial institution because it's very expensive. But like I will show you like, okay, this investment makes sense because, you know, like now the cost of wind or solar is not that bad. And then 5 years, 10 years, 20 years, we can get the revenue. So can I borrow money from your bank? The next step is you need to get a permission from the government. In this case, the government or regulator in the US is usually each market has, United States have different electricity markets, and different markets have kind of regulatory process you have to go through. But the most important process is, can I put my power plant here? Can I get a permit? Very simple question. But this requires a so-called study, okay? Because, you know, electricity operator want to think about, okay, if solar or wind comes here, how can I connect these guys to the main grid? What is the environmental impact? What is the cost? What is the implication to the grid system stability? They need to do the research and study, okay? So there's a process called this study. It used to be very quick because not so many power plants were built in the US. Okay, most of the time, you know, like a few power plants coming in, each of them are massive, but only a few. Now what's happening is, this is actually exciting and interesting. Lots of investors in the US want to build solar and wind because it's cheap enough and potentially profitable. But the thing is, regulation is very, you know, like delayed in a sense. They don't have capacity to sort out many applications, and they do the process, you know, built for fossil fuel power plants, but they do it for renewables. And so the renewables tend to be far away from the main grid. So there needs to be a bit more longer connection, like interconnection to the main grid. So this study kind of got cumbersome, basically. Cumbersome and so many applicants. But the outcome is very striking and disappointing. So now, if you think about 2023, this graph shows how many months do you need from application to the actual like a construction process. if you want to build a power plant in the US. And now it's approaching about 5 years, right? So, and probably this year, now 2025, this gets worse and worse. So maybe if I look at the new data, probably this is like a 6 or 7 years potentially. Okay, it's not getting better. So imagine like if you are ambitious, investor who care about environment also, but also care about profitability and want to build this plant here. Okay, when can you actually build? It's going to be at earliest 2030. Right now it's 2025. So if you apply now, 2030, you can build a power plant. What financial institution can give you money for that type of project, right? You cannot start building at least in 5 years. And after that, like how many years do you need to have to get profit? So this just makes investors' decision very hard. Also, financial institutions' decisions very hard. And this is nothing coming from the market itself. This is about the regulation. So there is now ongoing debate, like how can we make this design better? Okay. And some electricity markets in the US are trying to implement. Okay, but this is like one example. Nothing like this happened when we had fossil fuel power plants. Only a few are built every year. But now small scale renewables, they want to build more and more, which is great news, but regulation is just behind. Okay. Another example is from my paper with my co-author Mark Regwan. We wrote this paper in 2016. We looked at auction design in Spanish electricity market. And one thing I will just skip technical details, but maybe go over some overview. So in electricity market, there's interesting market mechanism. They actually do auction, so demand and supply. So demand meaning people who want to buy electricity, who want to, like utility companies, for example, they come to the electricity market to buy electricity. There are sellers, those are power plants. They're also coming to the market and they do the auction mechanism to sort out who should produce how much and when. Okay, and there is a day-ahead market. So suppose think about electricity delivery tomorrow at 9:30. Then there is electricity market today to think about it. That's what we call day-ahead market. There's auction mechanism, okay, and then this sets who sells how much and who produce how much, okay. But then there's some kind of uncertainty between today and tomorrow. If that's the case, they want to resolve the uncertain problem. So that's why usually electricity market have kind of intraday real-time markets. And in Spain, there is a lot of intraday markets. So this is a kind of market design in the picture. So if you think about electricity delivery, let's think about like 9 a.m. tomorrow, okay? Then first market will be 10 a.m. today. So like in 30 minutes from now, we're gonna have day-ahead market. But after the day-ahead market, there's another market, intraday 1, 2, 3, 4, and then get to the final delivery at 9 a.m. tomorrow, right? So this is what we call sequence of the markets. And the primary reason is they want to, again, kind of solve this uncertainty problem. So having more and more markets will be helpful. Again, this mechanism was built before renewables. So before renewables, most of electricity power plants are fossil fuels or nuclear fossil fuels. So like they have pretty much certainty about production, like how much they can produce because of their fuel availability, their technological availability. Okay. However, if you think about wind power plants in Spain, most of the renewables are wind. Wind has a lot of uncertainty about the production. Okay. So what we found was it seems like wind farms are actually exploiting this mechanism to get more profit. Okay. which may not be bad thing if you think about maybe wind should get more profit because of the, the reason we discussed. Maybe as externality is not priced, so maybe it's okay to give them more profit. So we're not saying this is just entirely bad or anything, but we found wind farms are actually exploiting this system. Okay, so we found that price of day-ahead market is usually higher, and then the final market, intraday market price is usually lower. Okay, and then what wind farmers doing is basically arbitraging between the markets. So they come in to say, I want to produce a lot, let's say 1,000. But then they come to the next market saying, I want to update my production. I actually want to produce only 500. And then next market, they say, I want to produce only 250. So they change the position, financial position along the market to exploit the price differences. So to make it very simple, basically they're doing some arbitrage between markets. And the challenging issue for the regulator is, if this is a thermal power plant, then regulator might say, what are you doing? Are you just changing your position frequently, even though you might have like a certainty about how much production you can do? But for wind, maybe it's really challenging because regulator might think maybe wind is just uncertain and they are updating their production quantity according to the wind prediction like the next day, right? So maybe this is a natural process they do, or maybe this is the arbitrage process they do to make profit. And our paper shows this is probably just making profit. And maybe one interesting thing we can show is this process the regulator kind of found out, and until 2012, wind farms had this incentives. So we see this behavior, arbitrage behavior. But at the end of 2012, regulators kind of shut off wind farms from this incentive. So wind farms in 2013, they didn't have any more incentive to arbitrage between markets because the price they get was not linked to the market price in 2013. And from the data, you can clearly see wind farms change their behavior clearly between 2012 and 13. Okay, so this is kind of another example I want to just deliver. Market design, regulatory design need to be updated to accommodate wind and solar because their characteristics are so different. And I think we are doing better, but still in the process of doing it. So the research way we do and the teaching we teach, we talk about this and kind of help us understand like what should be done. This is important to us, like economists, researchers, because we care about, but also think about policymakers and also private sector workers like, who are working on this electricity energy industry. Those issues are kind of first order. So that's what we care about, and then kind of we do research and teach. Okay. Next one I want to talk about insufficient intertemporal market integration. So this is about the time. Okay. So one biggest challenge is of renewables is probably you heard about intermittency of renewable energy. So this is one example showing solar PV production. Okay, so of course we know solar is producing during the day, no production at night. That's a problem too. But another additional problem is even within the day, solar production is so spiky and very, very frequent, like fluctuates over a minute and sometimes by second. This is because sunlight, usually most of the places, get distracted from cloud, right? So if that happens, production goes down, but if clouds go away, then production go back. And this frequent going down and going back is really challenging to the electricity grid. if there's any electrical engineer in this audience, I think you probably learned from college, okay? Electricity system needs to be kind of stable. Otherwise, this fluctuation of production will basically disrupt the system and change the frequency of basically this wave of electricity so much. And the challenging part is if there's some kind of damage to the grid in one location, usually large scale blackout happens, right? So if we make a mistake in only one part of like solar plant or wind plant damaging to the grid, it could generate large scale blackout affecting everybody in the system. Okay, that's why this is really fast order problem. And how can we solve this? And without large scale storage, this is challenging problem. But one good news is, again, we know that now our battery, like phone battery, is also getting better. I just got a new phone from high school, thank you. And this phone battery is much better than the one I had before. So I think battery technology is getting better and better. So same size battery can charge more, but also more importantly, this figure is showing the cost of battery is going down, has been going down. Kind of similar story to the one I talked about at the beginning about solar PV and wind. So here we have, let's say 2010, when I was a grad student, it was $500 per kilowatt hour, like a battery pack. Okay, $500 in 2010. Right now in 2005-ish, it's now close to, maybe you heard about, it's close to kind of $100. So we are already like 1/5, right? So the question is, how can we get even better? And for battery, I want to be optimistic, but compared to production cost of solar panel and wind materials, wind turbine materials, this part is really still uncertain and controversial. So some studies predict battery cost is also going down a lot, like very steep over the next 2 decades. So up maybe around 2040, we could have a dream scenario. Maybe this price is now is going to be like $10. So $10 per kilowatt hour. Okay, that's a dream scenario. Most pessimistic scenario is battery technology is a lot harder than solar panel or wind turbine to make a lot of progress. So maybe even at 2040, we're gonna be like around 100 or a little down to 100, so like $80. So that's a pessimistic scenario. And I think there are many studies around and we don't have consensus yet. One good news from our perspective is, as you know, we have now more and more electric vehicles coming into the market and lots of competition between electric vehicle companies. And they need very good battery. So my prediction is that would help R&D on batteries, and eventually that would actually help the electricity system. So suppose it gets to $10, okay? What would happen is this will not be a problem because we can use battery, right? So imagine solar generating this spiky production. If you have a battery, you can just store each minute, each second spiky production. And then from the battery, you can discharge to the grid, very continuous, stable amount of electricity, right? So battery can be combined with renewables to solve this problem. So that would be a fantastic scenario. And again, it's controversial, but I want to give you one more maybe optimistic picture. I study a lot in Chile, Chilean electricity market, because they are doing a lot of interesting things about renewable energy expansion. I will talk about for the last section. This is a data I'm showing from Chile. August 2024, what was the new power plant being built in Chile, and also kind of decomposition by sector. Okay, and you can see it a little bit. 53% of the new capacity of construction is from solar. So orange is solar, and green is wind, 10%. But what I want to focus today is this gray, 23% is called BESS, BESS, and 7.6% is FV plus BESS. Okay, so the gray BESS basically means storage. And pink FV plus BESS means actually solar PV, solar panel, and storage come together as a power plant. So a lot of new power plants in Chile are purely storage, that's basically battery, or solar panel with storage. Okay, so Chile is already in that moment building those power plants, zero emission, and potentially solving this problem because of the storage. So this is the future, I think, for other countries. So California, Texas are now moving toward this direction. We are seeing much more storage facility coming into the market together with renewables sometimes. So this is optimistic scenario. We will see how much reduction in cost we can get for battery. Okay. So for the last 10 minutes or so, I'll talk about the final topic, and maybe we can also go through questions after that. So in the last maybe few years, I have studied about this issue. So we already talked about insufficient intertemporal market integration, right? And this can be solved by storage, okay? But one more issue that cannot be solved by storage is this problem, what I call spatial market integration, okay? So I already talked about this a little bit. One issue about renewables is that the best location, if you think about best location for solar production, best location for wind production, they tend to be far from where we are or where we do business, right? If you think about cities or manufacturing centers, we are usually far from the best location for solar, which is usually like in the middle of the desert. No cloud, not so much of rain, almost constant, like full production. That would be great. Wind tend to be best in the mountain area, lots of wind, or maybe offshore. Okay, that's also like another place far from us using electricity. So there is basically spatial disconnection between demand and supply, if I use economics jargon. So this connection between those two will create this problem. So why I want to show you like how severe this is. So solar wind resources tend to be far away from demand centers. So this one showing in the US, for example, population center. Here is like New York, East Coast, Chicago, Los Angeles, Bay Area, Texas, maybe Houston. So those areas, population centers, where do we have the most solar power? It's a kind of this orange line, orange color. And the wind are best located actually in the middle of the country. Okay, I think the wind is pretty much a good example. Like best location to produce is here, but almost no one are there. Okay, almost no businesses are there. So we need to get those electricity to the place people use to connect to the demand. Solar is a little better. California, Texas is a better example, but still, if you think about best location of the solar, even in California, it could be like a desert. Then we have to connect to the city, okay? So what is actually happening right now? Right now, this connection is not enough or just doesn't exist. then what happened is this. So now we are actually throwing away a lot of renewable energy, even though it is zero emission and zero marginal cost, right? Completely marginal cost free and emission free. However, we are throwing them away. So this is called curtailment. In the US, I think on the left, we are looking at mostly solar in California. And on the right, we are looking at mostly wind in SPP, this is like southern states of the US. And you can see it, this curtailment amount is increasing a lot and a lot. And this is because they generate electricity there, but they cannot send it to demand center because there's no connection, or there's no enough connection. Then they have to throw it away, otherwise electricity system breaks out. So again, electricity system, supply and demand needs to be met each time, okay? So they have to throw it away. This is what we call curtailment, okay? You can think about if we have storage, maybe we can solve this problem a little bit. Yes and no. Yes, if this is an intertemporal problem, we can store and discharge when people need it. But if this is a spatial problem, you still need to deliver to other location, right? So that's why this is another additional problem we need to solve to expand renewables. So what's happening right now is in the US, what we call, this is interesting, negative wholesale prices. So some places in the US, if you want to buy electricity, you can actually get money because price is negative. Okay, it's because people want to throw away electricity, meaning we need to discard, right? So if someone can buy it, that's great. So market mechanism makes electricity price going down to negative, which is great for the consumer if there is consumer here. But also you can imagine from the business, this is really bad because if price is negative, who want to build wind power plant, solar power plant here, even though it's a great location? Okay, so this discourages investment, and that's a problem. So that's what our paper is about, and also what this is kind of considered one of the first order issues in the US energy environmental policy. Okay, so Biden administration had this bill, and then they talked about this issue as a first order issue. And I believe even though we had a policy change, I think this is still a key issue and priority in the US energy and environmental, especially energy policy, because even if you don't care about climate change emissions, this is basically not helping the business, right? If you think about economic growth coming from new energy sector, we can build a power plant there, but they cannot make profit. So this is a problem from the market perspective as well. So in this study, we actually look at Chile, because Chile did, in a sense, frontier thing before US in my mind, okay? So Chile has similar problem as I described about the US. So Santiago, beautiful city, is the center of the business, but this is far from renewables. So where is the best location to get renewables in Chile? It is in Atacama Desert. And if you look at Google Earth like this, it's interesting. You can see like a really, really tiny object in the middle of the desert in Google Earth and wonder like what this is. And if you can zoom in, it's a massive solar power plant station, okay? And it's really like in the middle of the desert. Fantastic view. I actually went there last Thanksgiving with my family. I wanted to see this in person. It's really spectacular. But the problem is this is in the middle of the desert, and it's about 1,500 kilometers from Santiago. Okay, so Chile had this problem back then until 2017. Here I'm showing a map of Chile, looking at price of electricity, wholesale price of electricity around noon, okay? And you can see it, this Atacama region in the middle has blue. So blue is price went to zero. It's because, as I said, solar production coming in, but there's not so much demand in Atacama Desert. And also the electricity cannot go to north or south. So they have to discard a lot of solar electricity in 2017. That's why it's blue. On the other hand, if you look at northern area, this is mining industry in Chile. They have like a yellow. So yellow is probably about 40 to 50 US dollars per megawatt hour, right? So this is 0 and this is 40-ish. And then even worse, if you look at Santiago in the south, Santiago people used to pay close to 70 US dollar in the wholesale market electricity, right? So the massive difference between regions within the country. So Chile recognized this is a problem. We have a lot of solar and solar potential in Atacama, but we cannot get just electricity to north or south. So they connected with the massive transmission line. First they did in 2017, they connected blue to the yellow, so Atacama to Antofagasta, mining industry. And then 2019, they connected Atacama to the south, okay, Santiago area, to basically try to solve this problem. So our study looked at this from like a data driven with economic theory to think about what was the implication of this policy. Okay, so as I said before 2017, there was no like big connection between north and middle Atacama. So they did an interconnection here. And then after that, they got another connection from Atacama to Santiago. So even before 2019, there was some line between Atacama and Santiago, but that was not enough. So that's why we call the 2019, another blue line is a reinforcement. They had another parallel line to get those things, those two places connected. Okay, so I have some trade theory to talk about theoretical perspective, but because of the time, I will just skip. By the way, this slide is on my website. If you want to take a look, everything is there. I want to focus on some visual evidence. Okay, so this is showing price difference between Atacama and Antofagasta. Okay, so desert region versus mining region. So before interconnection, they are not connected. So you can see it, supply and demand condition changes between those two regions, and then the price difference could go negative or positive, right? Because they cannot trade. But after this interconnection, those two places got connected, right? So finally, they are able to trade. So from the trade theory, we know this would make things better because now cheaper power plants can supply more, and then expensive power plants can take a rest. So this will show up in a price difference because after the interconnection, there's no price difference because they can trade, right? So this is the economic mechanism to make the kind of price equilibrium at the end, and you see like price difference basically gone, okay? Similarly, this is between Santiago and Atacama. Interconnection itself didn't do much, but helped. But also the big push was the reinforcement 2019. Basically, those price difference are gone in this period. If you're interested, you can also look at more recent years. Now they have another maybe good problem or bad problem they have, okay? In this paper, we stopped analysis here. But after this, because of nice connection, there are more solar plants coming into Atacama Desert. And now they have a congestion issue again. And then now Chilean government is actually planning to build one more line, okay, to get even more capacity. So this price difference, if you look at recent years, it's actually going up again, and they are now trying to solve the problem again, okay? But fundamental issue is basically the same here. And I want to show you also like in a map. I have 1 more minute, okay? And then we're gonna have another session, very 5-minute session, okay? So before connection, this is a map I showed the first, okay? And after the interconnection from north to Atacama, you can see it because of this connection, this yellow region got green. So price went down, and then this blue region got less blue, right? So from 0 to a little bit positive. And finally, when they connected everything, everywhere got kind of greenish, right? So not expensive, but not 0. So this would help Atacama producers to gain profit. So this would help them to invest more and more solar plant. That's basically what our analysis is about, okay? So time is up, so I will skip everything, but take a look at this paper if you're interested. But today, basically, I talked about 3 issues: regulatory market design, undeveloped, insufficient intertemporal market integration, and insufficient spatial market integration. I study many of them, but also a lot of my colleagues study those issues, very exciting new topics. And we also teach about those issues to think about with students how to solve this problem because we care. And a lot of economics and also data analysis. So this is an exciting area to study. So if you have any more questions, you can put that into the chat. But I also have an exciting announcement from Jess about the new master's program we have.
Thank you so much, Professor Ito. This is so great. Hopefully this was helpful for everybody to kind of get a feel for what it would be like to be, sitting in a Harris classroom. We know this is virtual and it doesn't have quite the same feel as being on campus, but is definitely, the topics and relevance that we hope that is resonating with all of you. On this same note, we are launching a new program coming this summer. So can everybody see my slides now? I just did a quick switch. Awesome. Thank you so much. For those of you that I haven't met, very briefly, I see some familiar names, so it's nice to see all of you today. I'm Jessica Gagel. I am the Director of Student Recruitment. Please excuse my voice. I think my allergies, I think it's climate change, but my allergies are getting worse and worse and worse. So this is why I sound like this today, but I am excited to talk a little bit about, for those of you that have a true interest in this area, in the intersection between energy, sustainability, economics, and the way that policies are written to support these. We have a new program that is a 12-month-long Master of Science in Climate and Energy Policy. It's going to be a deep dive into very specific coursework that is, mirroring our core curriculum. So you're going to get your data analytics, you're going to get your economics, but everything is going to have a climate and energy focus to it. It is a program that is going to start in the summer, which is new for us. Generally, we start in the fall. And the way that it's built is going to integrate both an experiential learning component and a capstone. So to just bring this into how would this look for anybody that's interested in it? We would have folks starting this coming summer in the core curriculum, which would be from July until August. We have a September immersion. So for those that are a little bit unfamiliar with the UChicago calendar, we don't start until the last week of September for classes. So we're quite a late start in the fall. And we will these students will be able to do an immersion trip in September, maybe more than one place. We're sort of having conversations right now around, where this is going to go, but some of the places that are being discussed are New York, to kind of look at the incentives and the rebates and sort of the economic analysis. Texas, because Texas is experiencing kind of climate change to, on all sides, right? It's got a lot going on down there. Also, the way policies are written, also fracking. And then potentially an international trip to India to look at how a developing country is really looking at sustainability and energy and environment policy there. Then those students would come back and be fully integrated with the MPPs and MAs and MS CAP students here, taking their autumn quarter, winter quarter, and spring quarter. So essentially you would begin in summer of 2026 and graduate in the spring of 2027. There's a mixture of electives in there. Those electives are going to be cross-listed across the university. So some will be Harris specific, some will be out of Booth, some will be out of the physical sciences division for those that have a real interest in like geo mapping. There are classes that are going to be available for that as well. This is also a unique program because it has a capstone. And so, MPPs can take electives that mirror a capstone project, but this will be a hands-on opportunity strictly for our MS CEP students. So I wanted to just kind of give a brief overview of that because this is really new for us. We're super excited to launch this program. And Blake, thank you. You put up the link that I was about to put up. Our application is open for this. The one note that I did want to say for those of you that are in the midst of applying right now or thinking about applying, the timeline for the MCEP is a little bit different because this is going to start in the summer instead of the fall. The final deadline to join us will be in January for these folks, right? So it's our round 2 deadline, which is January 15th. That's the final deadline for the MCEP. So if you're interested in it, I'm going to put my contact information in here. You are welcome to reach out to me directly to ask any questions about it. We have sessions about this. Obviously, we wanted to highlight Professor Ito's research area. Hopefully this resonates with you. This is a really important space for us, just globally to be right now, but to think about the way that economics and policy drive these decision-making factors. It's going to be more and more critical to have folks that are, working in this space and thinking about, solutions to these very complex problems. So on that note, thank you everyone for being here today. I know we're a little bit over time. Professor Ito, thank you so much for taking the time to bring your class virtually to students, and just stay in touch with us. For those of you that are interested in applying this year, please feel free to reach out to me directly or join us for another event. We're happy to kind of talk you through anything. Thanks everybody, and have a great rest of your morning, evening, afternoon, wherever it may be from where you're joining us. Thanks a lot, Blake, for organizing this. Great to see you all today. Take care.